Okay, um, I think we'll get started. Uh, thanks for coming. So my name is Peter Bandettini. We've been putting on a fMRI, or well, it started out as an fMRI course, and then it became like a neuroimaging course, at least for the past 10 years or so. So in one way or another, it became more formalized in the last few years, and at least in the last 5 years, lectures can be found if they're either in PDF form or in the actual lecture form online. I don't think it can be found at this moment online, but we're switching servers, so we're transferring things to the servers to be found online that way. And so we decided to mix things up again because people were giving more or less the same lectures, and since it was all online anyway, we thought we would try to do something slightly different. And so as you can see here, this is our schedule. Well, first of all, before I get into the schedule, so how many of you are summer students? All right. Wow, only a few. Maybe they haven't arrived yet. Maybe, well, who knows? But and so the rest, I guess, are postdocs and postbaccarates, I guess. So okay. All right. Well, so the goal of this course, though, is to focus. So I decided to mix things up a little bit and pitch it just a little bit higher, and meaning that we sort of delve into some of the issues more quickly instead of making it purely didactic. And we thought we'd focus on the controversies because the whole field is filled with controversies that are, everything from people making claims that are, a little bit beyond what they should, or people just having results that are not reproducible, or even I also sort of tone it down a little bit and talk about challenges. Challenges are things that we'd like to solve, but we haven't quite figured out yet, either the basis of some contrast or some other type of thing that's more of a challenge that's kind of rather than just purely a controversy. So and looking at the lectures, I won't go over all of them, but all of these people are at the NIH, and they're experts in whatever field they're talking in right here. And it goes everything from, open questions like, do we need big data? Do we need to have massive data sets? And what sort of studies led themselves to that? To, is multimodal integration really useful? If so, how? Everything to, just looking at how do we deal with multiple comparisons? That's something a little bit more direct. And then maybe more open-ended questions like, is fMRI just cartography? What can we actually learn about the brain with fMRI? So those are sort of more provocative things towards the end. So my goal is to have the lectures short, but today is kind of a long lecture because I'm just talking about, I realized as I was making the lecture that there's since bold and other types of contrasts are based on hemodynamics, there's a lot we've been doing to sort of push those limits, and there's a lot we don't understand. And there's a lot of false starts, a lot of interesting things in the field. So I'll just delve right into the talk right now. So starting out, it's going to be all about hemodynamic controversies and challenges. And I realized even in this talk, as I was preparing this talk, I realized that there's so much literature on many nuances of the controversies that there's just no way there could be a whole course on hemodynamic controversies. So just starting with bold contrasts. This part is not controversial for the most part, but there's a lot of unknowns still in this diagram. So bold contrast is basically based on the idea that with brain tissue activation, you have a vessel dilation that increases blood flow. And here, oxygen delivery exceeds metabolic need. This causes capillary and venous blood oxygenation to go up, and that also leads to a decrease in the amount of deoxyhemoglobin in the blood. And deoxyhemoglobin is paramagnetic, meaning it slightly attenuates the MR signal. So if there's less of it, the signal goes up because it's less attenuated. And that causes a decrease in intervoxel defacing, in which there's a certain type of contrast called T2 or T2 star, transverse relaxation contrast, that's very much related to the spin phase If things are in line, all spins are sort of in the same phase, experiencing the same magnetic field, the signal is high, but if they become dephased, it goes low. And that leads to then, so the spin phase increases a little bit, there's less susceptibility perturbers, and the signal goes up. And that's what leads to our bold signal. But the first controversy actually was related to this paper, Peter Fox. So when we first saw the fMRI signal change, initially there was a paper by Ogawa, who's one of the pioneers. Oh, by the way, you don't really have to take notes or pictures because all of this will be online. You can take pictures, don't worry. But I'm not stopping you. But I just it might be easier to just download it. Anyway, so one of the controversies here was that there's many in the field who was studying PET and other techniques that thought that with brain activation, the flow delivery, their oxygen delivery to metabolic rate would remain coupled. So there shouldn't be any increase in bold. So it was kind of a mystery why bold would go up. But also, as I was mentioning, with Ogawa, in his paper, when he first identified susceptibility contrast, he had one little sort of throwaway paragraph at the end saying, oh, and this might be able to show brain activation with increased metabolic rate, the signal should go down. So he wasn't considering that flow actually goes up, the response to brain activation. So this was debated for, I would say, a couple of years when it first came out, but then people finally agreed that this was the rough model for what happens. So with brain activation, you have increase in flow, causing an overabundance of oxygen delivered to the tissue, the active tissue. And that causes decrease in oxygen extraction fraction, which is OEF, which increases the blood PO2. And that leads to this. This is your basics of the signal change. You have a block design, which is about 20 seconds long here, where the signal takes about 10 seconds to go up. It takes a little bit longer to return the baseline. And I'll go into a little bit the controversies around some people observed pre-undershoots. We observe a lot of post-undershoots, and we still don't really know exactly the reason for the post-undershoot. There's different explanations for that. And also with a very short stimulus, you can get event-related response right here, which also has a post-undershoot. And then you can make movies as well. And it was nice that there was no controversy actually with fMRI kind of showing similar brain activation areas to PET. So this was an axial slice, a very, very early movie made of a time series of subtraction images in which the subject was tapping the right fingers, then the left fingers, then the right fingers and left fingers, and you can see very clearly the motor cortex. So this was great. There was no issues here in terms of localization. So the basic idea of the signal, before I get into some of the details, is that when you're collecting, this is a sort of a stylized version of how the signal should look. So when you're collecting data, you basically give an RF pulse to put the spins in the transverse plane, and then the spins decay. And this decay is either characterized by T2 or T2 star. Here it's basically T2 star. You just let it decay, and then our data is collected sometime during this acquisition. And during activation, there's a subtle increase in that exponential rate where the signal goes up a little bit. And so we're looking at that subtle difference right there. And so one thing to show, this is actually just that same diagram, but actually in a sort of a simulation. And so it turns out if you subtract two exponentials, the contrast looks like this. If you divide them and look at the percent change, it looks like this. And so one misunderstanding in the field, I'll also mention misunderstandings, is that, oh, it's great. So the percent change keeps on going up as you collect long echo time. So why not just collect a really long echo time and have the percent change be 100% change? It doesn't really work like that because what really matters is the contrast. So this peaks at the echo time where that is approximately equal to the T2 star decay rate that's known. So, and that's why when you at 3 Tesla, you collect data at a TE of 30 milliseconds or so, because the intrinsic T2 star of the tissue is 30 milliseconds or so. And you can look in great detail at this, and it turns out that and people don't really realize this as well as much, but these are a lot of contrast curves. This happens to be at 1.5 T, and this is at 3 T. And this is, each line stands for a different baseline T2 star. So if you have a really poor shim in some parts of your brain, then you have a really short T2 star, and you won't get nearly as much contrast as if you have a good shim. And because at 3T the change in T2 star gets larger, then you'll gain in contrast as well. But one early worry in the field is that the T2 star goes down with field strength. And the worry was that the T2 star would go down so fast that you wouldn't really gain any additional contrast. But it turns out that's not the case. And looking at the optimal TE, this is just a simulation. It's kind of controversial because it sort of suggests that there's basically kind of a linear increase with field strength, and it's somewhat dependent on vessel size, but I won't get into that. But it keeps on going up with T2 star as well. So if you shim really well, you get more contrast, and also higher field strength gives you more contrast to noise. So, and one other sort of, just to take this really far, I was talking to a colleague of mine at the latest meeting, and he was performing studies at 11.7 T, and he suggested that the contrast starts to level out even at super high fields because magnetic fields start to overlap, and potentially for other reasons too. But we don't know. We don't know. We have a human 11.7 Tesla scanner, so we have to actually compare that empirically. All right. So this pretty much summarizes all of the issues in bold contrast. You have basically you want to understand neural activation, and you're up against a lot of things. One, you're taking a brain and you're looking at the vessels, and you're dividing them into voxels right here. And each voxel contains a different blood volume. And so the magnitude of the signal will be different depending on how much blood volume is in that voxel and whether it contains veins or not. And you're passing through this hemodynamic filter, and you can look at all kinds of different things with the measured signal: magnitudes, latencies, correlations, fluctuations, transient undershoots. And then you have to fight against the fact that there's a lot of noise in the system. And it's everything from thermal noise to motion, physiologic noise, respiration, cardiac. I won't go into resting state today, but one of the big controversies is that one of the big challenges, I would say, it's more of a challenge than a controversy, is how do you really get rid of all the physiologic noise? We think we understand the dynamic nature of the physiologic noise, but when we try to model it and regress it out, it never works perfectly. We can never get pure functional MRI signal. So that's sort of an open challenge. And this vessel problem also becomes particularly problematic when you go to really high resolution and try to look to layer-dependent imaging, because there's a clear gradient in vessel volume from upper layers to lower layers. So upper layers are always going to have higher signal changes with bold than lower layers. And we have to somehow use another contrast that's more sensitive to purely capillaries, or somehow figure out a way to calibrate for that. Okay, so starting with just a rough overview of pulse sequences. So the brain is organized in many different spatial scales, everything from the systems level scale to where you're looking at visual cortex and motor cortex, all the way to layers and columns. And we're just starting to approach the layered columnar level of resolution. But looking at bold contrast, as I mentioned, it's nice that bold works. So this is some of the first experiments where toe movement, you see bold contrast at the top of the motor cortex. Finger movement is where it's supposed to be. And that made the field very happy. And that bold kind of works as far as that's concerned. Then people push things a little bit. This is some work by Ravi Menon looking at using their high field scanner, and also Kang Cheng using their 4 Tesla scanner. These are both 4 Tesla scanners. And it looks like you're able to get ocular dominance columns right here. This was, I believe, using more spin echo techniques. And it compares very well with optical imaging techniques. So one of the problems here is that there's no ground truth here. in terms of the locations of these columns, of these ocular dominance columns. You see stripes, you see a pattern, it's repeatable, but we don't know how distorted by the vasculature this is. And so while this will give you a pattern, it's still an open question of how distorted by the vascular structure these patterns can be. So we still need to do those experiments. So looking at perfusion imaging, perfusion came along about the same time as BOLD. And I was just looking this up. This will be part of the lecture in 2 days. There's a lot of different perfusion techniques. And they're usually characterized by the type of tag. You usually give an RF pulse to inflowing spins, and the type of acquisition you use, and how you do the subtraction. And these are 2 early techniques. One is called Epistar, one is called FAIR. The basic concept is that you give a tag, you have a control pulse, you subtract them, then anything that was flowing perfusing into the slice is revealed, and everything that's stationary is subtracted out. That's the basic concept. There's a lot of work that was done on this. This is a baseline perfusion map. This is the anatomic image. You have beautiful images. One of the challenges is actually to make perfusion imaging more clinically useful. One of the problems, though, with diffusion is that while it gives these nice maps, it takes a long time, a little bit longer than just injecting a bolus of gadolinium and measuring perfusion that way, but I won't get into that. Relative to BOLD contrast, it's always been known and appreciated that perfusion contrast is more localized, it's more specific to the area of activation because it's more sensitive to true perfusion, which is capillaries for the most part, whereas BOLD is sensitive to vessels and small and large vessels. Problem is that perfusion is extremely noisy. This particular map took about 7 minutes to make, and this map took about 2 minutes to make. So you can see the 2-minute one with BOLD is still much more sensitive than the perfusion. One other limitation of perfusion imaging is that it is limited to a plane in the brain, and you have to apply an inversion pulse and then to inflowing spins to allow them to flow into the perfusing area. So you have to wait for a second, and so on. And so it's slow, and it's only limited to a few planes and a few slices in the brain. Still, there's ways of potentially going to whole brain, but it's tricky. But if you look at it, the perfusion is really localized to specific areas where the BOLD is highly weighted towards large vessels. One other potential advantage of perfusion, though, is that when comparing the contrast to noise relative to BOLD in terms of activation frequency, like on-off frequency, BOLD always beats perfusion almost with every single paradigm, except for really, really slow paradigms. So there was a really nice study some years back by Jeff Aguirre, in which he showed that you can give a perfusion scan to a person one day when they're tapping their fingers, give it to them the next day when they're not, and subtract those images and get really nice perfusion images. This is an example. This is arterial spin labeling, 24-hour difference. So basically perfusion is really stable. It's much more stable over time than BOLD, as far as that's concerned. But it's really low sensitivity, though. Okay, let's jump into spin echo imaging. Spin echo imaging is basically involved with where you give an RF pulse, 90-degree pulse. This is basically the T2 star curve where you collect typical gradient echo imaging. And then you can apply a 180-degree pulse, and then basically that reverses the precession of the spins so that all the spins that went out of phase become back into phase. It's like running around a track one direction, and then suddenly you're told to run the other direction. All the faster runners will catch up with the slower runners, and they'll go back in phase. But not completely. And there's a lot of reasons for this incomplete recovery, but one of them is susceptibility perturbers. And it turns out that the smaller the perturber, the more it's on the scale of how far a spin diffuses in this time, the less it will be the less it will be refocused. So if you have a big perturber, it will be refocused a lot, and you won't get much activation contrast. So I'll skip this slide because I said what I just said. Basically, these are simulations where you have spin echoes with large vessels that get almost completely refocused by the spin echo, whereas with gradient echo, it becomes completely dephased. Right? Whereas small perturbers are not dephased that much. So you want to get something that's dephased optimally so that when it changes susceptibility, it will show the most change. Okay, so this is just using gadolinium, comparing, using a simultaneous spin echo and gradient echo sequence. You can see that that the spin echo sequences are much more sensitive to, it looks like looks more like gray matter. With gradient echo scans, it looks more like it's around large vessels. And this is with gadolinium. And this sort of summarizes the contrast between spin echo and gradient echo. And this is why everyone says, oh, spin echo is sensitive to small compartments. Because this compartment size is about 3 to 15 microns, which is about the size of a microvessel, capillary to a microvessel, whereas with gradient echo, it's sensitive to those, more sensitive to those actually, but it's also sensitive to the big vessels. The problem with this statement is that it's true mostly for when you inject a big bolus of gadolinium, which has a large contrast, which completely removes the intravascular signal. However, and this is sort of not really a controversy, I should sort of say it's a misunderstanding in some sense by the field, is that big vessels have lots of small compartments inside of them. So when using with bold contrast, when you apply a spin echo acquisition, if you still have intravascular signal, which you do at 3 Tesla, you'll get a lot of this small compartment, which is red blood cells, which are 2.5 microns in diameter, dephasing. So you'll get big vessel effects because there's an intravascular signal. And still to this day, people say, oh, spin echo sensitive to small vessels. And yes, that's true, but it's also sensitive to big vessels with intravascular signal. At 70, that's a little bit less of the case, but here's an example of a gradient echo signal being sensitive to a large vessel right here. But also, when you look at spin echo, it's also sensitive. There's one other reason that I'll get into in a second why it's also sensitive to larger vessels. But first of all, this is just, I don't really want to go into these plots that much, but this is the amount of intravascular signal in blood across field strengths. I made these simulations some time ago, so it only goes up to 4 Tesla. But typically, when you do a spin echo acquisition, you collect about 50 milliseconds to 100 milliseconds, and so there's not much left. It's still only 0.1, but it's still there. So you have to always be a little bit careful with that. And also, the fact that this T2 star or T2 effect causes the blood to have a much lower T2 star than tissue, than gray matter, that's the basis of most of our venogram contrast, where you just do a T2 star weighted image and you see all the veins as these dark lines. And that's why. If you try to do a venogram at 1.5 Tesla without additional analysis of the phase changes, you wouldn't get any contrast just looking at the T2 star weighted curves. Okay, pros and cons of spin echo. So increased specificity, especially at high fields where intravascular signal is low. It's less sensitive to rapidly flowing blood because there's 2 RF pulses with a spin echo. Give an RF pulse to one. If you have really rapidly flowing blood, it flows out of the plane before you give the next pulse. And less signal dropout. Because spin echo refocuses all these big susceptibility gradients. So the images always look a little bit better as far as the anatomic images. Less slices per TR, takes a little bit longer to acquire. Much lower functional contrast. And this is the big thing also. The acquisition window in most echoplanar spin echo is long. Only the pure spin echo occurs at exactly the point where there's a spin echo. But when you acquire your data, it takes 30 milliseconds to acquire the data. So you're sampling the T2 star contrast portion of that curve during your spin echo with echoplanar imaging. So that's another reason why spin echo is not really a good answer, at least with echoplanar imaging, to looking at small vessels. And once again, very large intravascular signal is still present at almost all field strengths. So I would probably try to do a very pure spin echo at 7T if I were trying to go to high resolution, but also maybe some other sequences which I'll mention. Another sort of not really controversial technique, but sort of a boutique technique called velocity nulling. It's one way of getting rid of the intravascular signal. So any rapidly flowing blood will be dephased by adding diffusion gradients. And that pretty much gets rid of all that signal right there. And there were early studies that showed that this is that 1.5 Tesla where the signal actually was attenuated. The activation percent change was attenuated by about 2/3, meaning that 2/3 of your signal comes from the intravascular signal. Problem with that is that when you add greater and greater amounts of diffusion weighting, the signal almost goes away completely. And so that's always a big problem. So anyone trying to do spin echo with diffusion weighting, they won't have any contrast left to actually see much of activation, even though it's probably close to being capillaries. So a recent technique that emerged is called vaso. And that was invented by Hanzheng Liu, who's now at Johns Hopkins, and it basically involves, and I'm purposely not really getting to many pulse sequence diagrams right here, but it involves essentially relying on the fact that the T1, the longitudinal relaxation rate of blood, is different than tissue. And if you give an inversion pulse, you can wait until the blood signal basically goes negative, and then it goes through 0 and then back up again. You wait until the blood signal goes through 0, and then you give an excitation pulse because your gray matter has a little bit faster T1 and there's some signal left. And so you're imaging where there's a blood null point. And if you have an increase in blood volume, you'll have more of that null signal and the signal will go down with activation. And that's what occurs. So once again, the local problem, a problem with looking at bold contrast with grain echo imaging is that it's great for making these macroscopic maps. This is sort of an analogy. My postdoc Renzo Huber came up with this, of looking at CO2 emissions. You can have nice big blobby maps of CO2 emissions across cities, but if you actually drill down and want to look at CO2 in neighborhoods, the problem is that a lot of it's contained on roads and so forth, and so you'll only be limited to looking at the road effect with bold, whereas you really want to get at what's going on everywhere. And so that's why with bold you get these large blobs, but if you try to go to high resolution, all you're going to get are these vein effects. So he did this pretty nice analysis of the relative sensitivities, and this is actually from a paper that he referred to, though he did analysis late after this, but of the sensitivities of various pulse sequences. He found that, of course, bold was sensitive to large vessels, has a lot of contrast, and that's why people still use it. It has by far the most contrast. It's the easiest to do, the functional contrast. But vaso actually, which is sensitive to, it turns out that, and this is still kind of a controversy in the sense that people don't really understand why, that it turns out vaso, the blood volume changes, are much more localized to small vessels and capillaries. One would have thought, including myself, that vaso would be, large vessel distension, which would still be a problem. It would be downstream large vessel effects. But that seems like it's not the case. So it's still kind of an unknown. And once again, these are various other types of spin echo techniques. And they're certainly sensitive to small vessels, but especially diffusion weighted, but there's no contrast left. And this is sort of a measure where he tried to look at specificity versus selectivity. And all of these sequences sort of fall along this curve, except vaso kind of jumps off it. Without going into it, there's other pulse sequences that are spin echo-like, one called Grace, that also kind of jumps off this curve. The problem is we don't know exactly why it does. It's still sort of a spin echo technique, so it's more of a pure spin echo, but it seems to show more sensitivity than regular spin echo. So that's an unknown. All right, but once again, if you have diffusion weighted T2, which is spin echo with diffusion weighting, you have nothing, absolutely nothing left after a lot of averaging. Okay, and vaso basically is good. I'm going to zip through this because you'll hear this in future talks, but it's basically good for going to resolutions of down to 0.75 millimeters, where you can start to resolve layer-specific activation. And this is sort of a challenge now in the field because vaso is sort of like perfusion imaging, where it's limited to a single plane or just a few slices in the brain. But it's very sensitive. You can see actually with these different paradigms, you have different shifting of the layer sensitivity right here, where you wouldn't really get that with just pure bold imaging. And you can get down to extremely high resolution to resolve digit activation in a way that bold could not do as well, because it's so weighted by the vasculature, whereas vaso seems to work really well. And the reason why it works so well, once again, is not fully understood. We know it's sensitive to vessels, or small vessels and capillaries, but we don't know why it's so much better. It seems like it works a lot better in that regard. Okay, the rest of this will go relatively quickly, but temporal resolution has always been something that the field has pushed against with fMRI. And to start out with one old controversy, it's sort of the opposite of temporal resolution, and that is how well the hemodynamic response stays elevated during a continuous task. And this was a paper that basically showed that bold stayed elevated for up to 25 minutes, as long as a person was seeing visual checkerboard stimulation. There was another paper in the field, though, before this that claimed that habituated after 4 minutes. And it was a big deal in the field because they thought, oh my gosh, we can't give stimuli more than 4 minutes because the hemodynamics recouple themselves and the signal goes back down. And so it caused some concern, and it just shows that it takes a while for these things to be resolved. And basically, in those paradigms that were used in that other paper, they used activation that actually caused the neurons to habituate. And that's one of the ongoing challenges with fMRI in general, is that how do you differentiate from a neuronal effect versus a hemodynamic effect? In this case, it was purely a neuronal effect. Luckily, the hemodynamics stay elevated the entire time, as long as you have activation. So now going to temporal resolution, turns out when you give a very brief stimulus, you can elicit a response that is measurable. And so far, it's been shown that there's no real limit to how brief you can go. We've gone down to 16 millisecond visual simulation. We still see a response. Any lower, you almost don't get much neural activation. So that's a nice thing. That was never controversial. So one controversy, though, in terms of temporal resolution, that still is a misunderstanding today, and that is that if you were to look at an activation and make a map of latencies in let's say, just the motor cortex, you see that the latencies, as measured by the shift of the hemodynamic response, either plus or minus in time, latencies show a spread of plus or minus 2 seconds. And so that's a large problem with fMRI. Even though it's sluggish, if there were there we go. Even though it's sluggish, it's also very variable over time, depending on whether it's over large vessels that are downstream or not. And what people have tried to do is look at causality between different parts of the brain. If they saw a brain area turn on first and then another brain area, they would say, oh, that area is affecting this area because it turns on first. Well, in fact, it's very easy, depending on how you pick your region of interest, to cause an area to appear like it turns on first or not, because there's so much spatial heterogeneity in the vasculature. And so just looking at the distribution, it's pretty much plus or minus 2 seconds right here of the latencies. So that's sort of been not really a controversy, but a big misunderstanding in the field, as far as people trying to apply, for instance, Granger causality based on latency. It's just completely not useful as far as that's concerned, because of this underlying hemodynamic variability. And so one could kind of look at the problem in this way. This is sort of the spread of variability as a function of space and time. So let's say this is a point where the neural activation and point in time where it's occurring. As you go to capillaries, as you go to veins, it spreads out both in space and time. So, and there's no getting around that unless you localize more to capillary effects, which then are more contained in both space and time over the brain. So this was a really old paper, that an old book chapter that sort of summarized every aspect of temporal resolution. And what's interesting is that not much of this has changed. This has changed, and I'll talk about this in a second, how fast you can go on and off, which is related to nonlinearity of the response. Initially, we thought it was only 2 seconds on, 2 seconds off. Turns out you can go faster than that. But what's interesting, though, and this is sort of a challenge and maybe a controversy, is that it turns out that the standard deviation, if you were actually to take repeated measures over time of an event-related response, it turns out the onset of the response, it shows much less standard deviation of variability than the return to baseline with an event-related response. And it also, it turns out, there's other papers that have shown that during the onset, the signal, the activation signal, is more localized. So if you're trying to push your spatial and temporal resolution, you might want to limit your analysis to the onset of the curve, of the hemodynamic response curve. Okay, and this is just to reiterate one of the previous controversies. This is a study in which the right hemisphere was first turned on 500 milliseconds before the left hemisphere in a flashing checkerboard. And if you take a region of interest, if you just pick your regions of interest just right, turns out that you can get a difference in signal during the onset, or the whole thing. Problem is that if you actually look at the map of latencies, you can't discriminate between right and left hemifield just looking at that map. And if you reverse the order, you can't really discriminate looking at a latency map. So that's just to bring home my previous point, that without a control, you can't make maps of latency that are useful below about 4 seconds in difference. And so, but if you subtract these maps, it turns out the hemodynamic response is extremely well behaved. So this is potentially a challenge in terms of one way of calibrating the hemodynamic response. Just modulate your paradigm timing. It won't give you absolute latency, but it will give you relative latency change, which you can get down to about 50 milliseconds or 100 milliseconds. And this is actually going down to 250 milliseconds. You can still see somewhat of a difference. Once again, though, you can't see any difference just looking at the latency map from each individual timing. And there's all kinds of other issues, pulling out the hemodynamic responses that are wider or more delayed. And I'm not going to go into this too much, but basically there's all kinds of paradigms that are trying to look at either bottlenecks in processing or upstream processing based on the delay or width modulation of the hemodynamic response. The reason why this is controversial is because since this paper, there's been a couple of papers in this, but really the field has been completely silent in terms of trying to push the temporal resolution in this way and interpretability of the signal. It's just really hard to do. And this is a simulation basically saying that in an ideal world, if there were no hemodynamic delays whatsoever, if there were no spatial variations in the hemodynamics over the brain, and everything behaved exactly the same, if you're just limited by signal to noise, which really that's a main limitation. It's not the fact that the hemodynamic response is slow, it's that it's variable and you have noise. And if you're just limited by the signal to noise, considering typical fMRI signal to noise time series, it turns out to differentiate onset times of using a paradigm in which you had, for instance, 8 seconds on and 8 seconds off, so you're always driving the hemodynamic response like a sine wave, you can actually differentiate down to 100 milliseconds after averaging for 11 runs, which is about an hour of averaging. So you average for an hour, you might be able to differentiate down to 100 milliseconds with this typical temporal signal to noise. And this is an ideal world where there's no hemodynamic variability. So it's really tough to push it down below that, if at all. One clever sort of paradigm that, once again, is sort of a challenge and a controversy because it's not been reproduced that much since, but it's really a nice idea, is that of looking at relying on the fact that if networks nodes send inhibitory inputs to other network nodes, you can actually adjust the timings. In this case, this was a paper by Ogawa with rat forepaw stimulation. And he basically stimulated one forepaw and then waited everywhere between 50 milliseconds and 150 milliseconds to stimulate the other forepaw. And he simply measured the induced slow, bold response. And he found that if he made the delay just right, which was 50 milliseconds, this forepaw activation suppressed the activation on the other forepaw hemodynamic response. And he found basically he was able to measure sort of the net communication time between left and right forepaw. So this is sort of a way of pushing the temporal resolution a different way. It's controversial because nobody's really repeated it that much. Maybe it's just hard to find inhibitory network nodes that are modulatable, but still it might be worth looking into. Nonlinearity. So this is known in the field. It's not really controversial, but it's an important point that the signal, the hemodynamic response always seems to show more amplitude with very brief responses as you would expect from a linear system. So at about 2 to 5 seconds, it starts behaving more linear. So this is actually a measure of the, essentially the amplitude difference between what's expected versus what you actually get versus stimulus duration. So when you stimulate for anywhere from 0 to 2 seconds, the system is extremely nonlinear. There's much greater response than expected. That observation is not controversial. The reason for it being nonlinear is relatively unknown. It could be neuronal, it could be hemodynamic. And what's curious is that the opposite sort of happens for off periods. So if you modulate your off periods, for a very brief off period, the hemodynamic response kind of stays elevated longer than you would expect from a linear system and becomes more linear as you increase your off periods. So that's also, looks like this, a mirror image of this almost, and it's not clear why. So for instance, this is some work in which we had various paradigms of different duty cycles, and we found that the amplitude of the hemodynamic response after the duty cycle of activation was deconvolved, you get larger amplitudes with the less time you have a stimulus. And the more time you're driving the system, the amplitude starts to habituate. You get a curve that looks something like this, where it becomes either sublinear at longer duty cycles. Trying to simulate this, you can create sort of this curve. I'm not going to go into it by modeling using the balloon model, by implying that there's not much of a change in extraction fraction or blood volume. You can also create this curve using just a purely neuronal model of the neuronal input, in which you have an initial transient, an off response, and a refraction period. You can get this same response too. Right now, that's sort of unknown. You have a hemodynamic explanation for this nonlinearity, and you have a neuronal explanation. And both are probably compelling, and it might be a little bit of both. So here's some, once again, just empirical work by Logothetis showing that there is always this large transient in the neuronal response that occurs that causes the hemodynamic response. And this is the data I just showed you, and this is the data I just showed you. Here we tried to simulate that nonlinearity purely by a neuronal transient. Turns out the neuronal transient has to be a lot larger than what's typically measured in electrophysiology. So it's probably also a hemodynamic explanation. But the answer is murky. So here's another type of nonlinearity. This is sort of static nonlinearity. So, and this is actually really sort of a positive thing for bold contrast, because this is also from Logothetis. This is a classic work. This is probably one of the most cited papers in fMRI, in which he systematically varied the contrast of a flashing checkerboard from 12% contrast up to 100% contrast. And he simultaneously measured with electrophysiology multi-unit activity, all frequencies, and then local field potential, which is a little bit lower frequencies. And he found that they locked into each other in a kind of almost a linear fashion. So there was a solid relationship, especially with local field potentials to bold contrast, solid linear relationship. What he didn't mention in his paper, which is just blatantly obvious here, is that this curve does not go through zero. There has to be a clear, huge nonlinearity right here. So this means that this is implying that very low levels of neuronal activation cause much, much higher bold responses than you would expect from the neuronal activation measured with electrophysiology. Which is actually kind of nice because you can actually be very sensitive to maybe like really low levels of like attention modulation, which has been shown as well. So in other words, bold is very sensitive to low levels of neural activity in a way that's highly nonlinear. All right. And that's still, I wouldn't really say it's controversial, but I would say that it is not fully appreciated, I think, in the literature. So here's also another type of nonlinearity. Well, this part shows no nonlinearities here. So this is basically an old experiment in which we tried to drive the hemodynamic response on and off at different on-off rates. And we find the amplitude of the hemodynamic response is not really compromised until about an on-off rate of 12 seconds on, or 6 seconds on, 6 seconds off. Then it resembles a sine wave, and then it becomes saturated in the on state. And we couldn't really follow it beyond 2 seconds on and 2 seconds off. Okay, so this is sort of an example of how something you feel is settled in the field. You look at that and you're like, oh, that's pretty settled in the field. But then someone comes along and tries the same experiment again. And this time, John Polamini did an experiment in which he averaged much more than these people did, this experiment, and which was actually us, but he did a better experiment than us in which he averaged a lot. And he found that even down to 0.75 hertz, almost, I was just even talking to him last week, he even sees something at 1 hertz, his group. Lara Lewis was the first author of this. At 1 hertz, he sees a hemodynamic response keep up. And the amplitude is such that it's extremely nonlinear effect. You would never expect given the hemodynamic response function, you would never expect it to keep up. But it does. So there's some other mechanism that's happening rapidly, that's occurring if you're driving the system that hard, that we don't know, that we really don't know. So it's still not quite fast enough to be really useful to look at neural activity, but it's pretty darn fast. At least it's heartening, though, and this is what I was suggesting. With all these nonlinearities of the hemodynamic response, it's linear enough so that you can do your jittered event-related activation paradigms and deconvolve the overlapping hemodynamic responses. So this is a classic paper by Anders Dale showing, giving 2 stimuli very close to each other, then 3, and he was able to, look at the combined effect, but then subtract the first response from the others, and he gets something close to a hemodynamic response. So for all practical purposes, between a stimulus duration of about 1 or 2 seconds and 5 seconds, it's linear enough. So you can do deconvolution. Okay, pre and post undershoots. All right, I have 10 minutes left. All right. People, the whole field, especially the physicists, love to talk about the pre and post undershoots. There has been a lot of papers about them, about what it means, what it could mean, do we see it? Especially the pre-undershoot. I'll start with the pre-undershoot. That was first identified in the mid-90s. But the problem is nobody, including myself, or not many people at all, could reproduce the result. A lot of people looked very hard. They couldn't see a pre-undershoot. One person that was able to systematically reproduce the pre-undershoot and modulate the pre-undershoot in animal models, Sanji Kim, was able to do it only by lowering systematically the blood pressure of the animal down to extremely low levels, which weren't healthy, to be able to increase the pre-undershoot. And I'll get into the possible explanations why. The post-undershoot is commonly observed. It's observed everywhere. But there's different explanations for the post-undershoot. And so with the first explanation, this is a slide by Arnold Willinger, is that the pre-undershoot presumably could be caused by the fact that metabolic rate increases a little bit before flow has a chance to kick in. It could also happen, though, I mean, any one of these are interchangeable. You could have an increase in blood volume before metabolic rate kicks in, or you could have an increase in velocity. So the post-undershoot also, the big controversy with the post-undershoot is that people have made simultaneous measurements of CMRO2, CBV, and have found that, and also flow, and also perfusion, and have found that potentially, so the first explanation for the post-undershoot was that blood volume stays elevated longer than blood flow. So blood flow goes down, blood volume goes, or blood oxygen, then metabolic rate. And so the signal would show a decrease in signal because the oxygenation is still the same, but the blood volume is higher. Another explanation is that metabolic rate stays on for a little bit longer while all the hemodynamics return down the baseline. That would also pull down the signal. So the two groups have these explanations. Also, people have found that there's different time constants there's a fast and a slow return to baseline in blood volume, so it gets even more complicated. So the bottom line is that people have tried to model it as well. This is some models by, I believe, Rick Buxton, showing, if you vary things a little bit, CBF stays elevated a little bit longer, or CBV stays elevated a little bit longer, you get a post-undershoot. You can easily create post-undershoots by modulating the timings of these essential components of the signal. So that you can simulate it, but I don't think that it's really been settled upon what causes the post-undershoot. And it seems like an esoteric point, but it's somehow a lot of people still think about this and talk about this and potentially try to use it as a way of maybe being more specific to brain activation or identifying disorders or whatever. So this was a slide that sort of summarizes what I just said. So initial dip may be due to temporal mismatch between increased CMRO2 and CBF, maybe due to increased CBV relative to CBF. Most people actually, I think, doesn't think it exists at all. Post-stimulus undershoot, it could be a sustained CMRO2, sustained CBV, like the balloon model, Rick Buxton's balloon model, or a reduction in CBF, which would also draw it down. So I didn't even mention that it might purely be a neuronal inhibition. So you could have neuronal activity suppressed, causing a reduction in CBF, which would cause the post-undershoot as well. So it could be a refractory period as well. So it's open-ended. Okay, really quickly, negative signal changes. This has been a wide open area of the field, and just somehow I included this, but so basically, there's one study that's kind of nice, and it's still not completely agreed upon, but it's one nice set of results. So Logothetis actually measured local field potentials, which are within a certain range of frequencies. But this basically was a study where it was simultaneous EEG and bold, looking at specific frequencies corresponding in space to where the bold signal either went up or down with specific tasks. And they found that low frequencies, 10 hertz and 15 to 30 hertz, corresponded spatially with a decrease in bold, whereas upper frequencies, 60 to 80 hertz, gamma frequencies, corresponded to the increase in bold. So I think the field is converging on agreeing on this, but I keep on seeing literature where it's not exactly correct, where it's not exactly this. So there's still some mystery as to what exactly corresponds to what in terms of, I mean, there's more, it's even more of a mystery in terms of, and I didn't show any slides in this, looking at layer activity. People suspect that feed-forward layer has a different neural feed-forward activity from upper layers has a different electrophysiologic frequency than feedback signal. So that's another thing. It's not just simply a simple model of activation versus suppression. It's feed forward versus feedback as well. So it gets complicated. Probably depends on how spatially removed the areas are that are feed forwarding and getting feedback as well. I'm not going to go into this, but this is basically summarizes all the ways you can have a positive bold, all the ways you could have a negative bold. And you can have a lot of different combinations of these to cause these effects without going into too much. You can study this or look at this afterwards. So one last point that I wanted to bring up is along the lines of what we might be missing when we do our activation experiments and when we apply a model. Usually with activation, you apply an input model based on your hemodynamic input or based on your neural activity. You give a checkerboard, you have a boxcar, you convolve it with the hemodynamic response, and you use that as a regressor to pull out the signal. Problem is that our models are probably way too simple. And this is just one really nice example by Camille Uludag showing, okay, typically you have a checkerboard. This is one of the most classic experiments where you have a flickering checkerboard that's either right hemifield or it's left hemifield. And so you expect, as many has shown, that if you give a right hemifield, looking at the blue curve, that's the hemodynamic response to one hemifield and then the other. If you use that as a regressor, you get very clearly one hemifield activation and then the other hemifield and so on. But it turns out, and this happens to be only one side though, but it turns out if you actually add transients, if you add transient activation at the beginning and the end, you don't get the hemifield specificity at all. You get a bilateral activation. So my suspicion is that there are many transients, and there might be time-locked in different ways that correspond to activation all over the brain that we're missing by simply applying one or two models to our data. And just want to end with showing this experiment. And so this, I would once again say, it's not really a controversy, but it's more sort of like a misunderstanding in the field that they just apply their simple model. They might shift the phase a little bit, but then they settle with that. But there's so much more going on. And also, of course, there's insular activity as well, it looks like right there. This is an experiment by Javier Gonzalez-Castillo in which he averaged one subject. He had 3 subjects, averaged them for about 9 hours, not all at once, just having them come back in the scanner and doing a very simple visual motor task in which they stared at the checkerboard, and whenever they saw this faint image of a letter or number, they pressed a button. That's just to keep their attention more or less constant. And did that for 9 hours, 10 different visits, averaged the heck out of the data, and did basically applied various different models to the data. But one of the models was just a simple hemodynamic response. One is putting in transients. Another one is just applying a function such that it captures in this wide net anything that's time-locked in any sort of way to the task and the stimulus. And from that data, to make sense of that data, he basically did k-means clustering on the final data. And what we found was this, is that with that most broad type of modeling of the data, of this very simple visual motor task, essentially the whole brain is active in some way. So, but if you actually look at the hemodynamic responses, they're all over the place. There's positive ones, there's positive transients, there's negative ones, there's things in the base of the brain that go all over the place. So all of these, I mean, while they're extremely faint, and they don't follow any, what I would hypothesize is a model of what to expect from the hemodynamic response. And also they're not motion. They're not like rapid, like just sudden changes. And also they map out in a way that's non-random. So you can see very clearly subcortical areas differentiated. You see the classic motor and visual areas that show up in the standard canonical response. But you see all kinds of other things. So I might call this controversial, but we haven't received much pushback from this. And I think actually this understanding is beginning to show up more in literature in which subjects view naturalistic stimuli. It's very hard to model naturalistic stimuli. You assume that subjects are doing whatever, and the only way to pull out that data is to look at the cross-subject correlation with the same stimulus. So here's an example of something that's sort of Not fully, I think, appreciated. But at the same time, there's more activation there. So just to end with a summary of all the factors that influence the fMRI signal magnitude and timing. There's physiologic factors, baseline flow, oxidation, volume, vessel size, metabolism, hematocrit, blood pressure, cardiac function, respiration, drug effects. And we don't really have a good gauge on the relative significance of these. It might be more depending on what study you're doing. Of course, you can modulate the sensitivity with different MR weightings. And of course, we don't fully understand or appreciate what aspects of neuronal function we're actually looking at. They might be looking at gamma frequencies, we might be looking at inhibition, excitation. It might have very much be a function of neurotransmitter concentrations, different timings as well. So all this is sort of an unknown as well. With the MRI, you can actually specify some of the physiologic factors, and you might be able to also rule out some of those so you can actually look at more neuronal factors, but that's still an ongoing process. So with that, I'd just like to end and welcome any questions. Thanks. So it's hoped also that in the following talks they won't be so long, and that was my own fault. I could have probably shortened this, but I really, the whole goal of this whole course is to encourage discussion and questions. If you don't ask any questions, then we feel we haven't engaged you or something. So, and that's our failure. But definitely, if you have any questions, don't feel pressure to ask questions now after I just said that. But please ask. And I'm always happy to take emails afterwards as well. And once again, these slides will be available online within a couple of weeks. So, okay, well then, in that case, I'll see you in a couple days.